Solving absolute value equations. In the previous exercises, we learned how to graph absolute value functions. The purpose is to help us with the algebra related to solving absolute value equations. The equation we're going to start with is a very simple equation, absolute value of x equals 3. It shouldn't take long to recognize that there are two solutions to this equation. One of them is x could be 3, the absolute value of 3 is equal to 3, or x could be equal to the opposite of 3. If I continue to solve this equation here, I would say x equals negative 3. This is logical because the absolute value of negative 3 is also equal to 3. So as far as the algebra is concerned, to solve an absolute value equation, we simply remove the absolute values and consider two possibilities. One possibility where what was inside was positive, in which case I leave it alone. This is based off the definition of absolute values. The other situation is what's in the absolute value is negative, like negative 3, but we have to take the opposite of negative 3 to make it positive. So we see two solutions based off the definition of absolute value. So again, right here is a summary of how to solve absolute value equations using algebra. You write two separate equations, one where we leave everything alone and just remove the absolute value, and the other where we remove the absolute value, but then take the opposite of whatever is inside. Then there's the graphical approach. You can see in black we have the y equals the absolute value of x graph, which is the v graph, and we also have y equals 3. So what this graph is a picture of two separate equations. One of them is y equals 3, and the other equation is y equals the absolute value of x. And so when we see the equation y equals the absolute value of x plus 3, we could look at it as two functions, y equals 3, the horizontal line, and y equals absolute value of x, that's the v graph. And then we can see two intersections, the intersection of the positive or increasing line with y equals 3, and the intersection of the decreasing line with y equals 3. And that's where we can see on the x-axis the two values for x that make this equation true. I have a Java update available. Anyway, so when we solve absolute value equations, we're going to have to look at the algebra, which is an algorithm that says get two equations and solve them both. And then we're going to back that up with our geometry, which is a graph of the left side and the right side of the equation and looking for the intersections and where they occur. It's a very simple example, just like the previous one. The only difference between this equation and the previous is the absolute value function on the left-hand side is shifted to the left 4. So here we can see the graph of the absolute value of x plus 4, and here we see the graph of y equals 5, which is a horizontal line. So when I use the graph, I can see that there are two solutions to the absolute value equation. One of them is 1, and one of them is negative 9. Both of 1 and negative 9 are 5 units away from 4. So they're equidistant from the center point. Now, as far as the algebra is concerned, to solve this equation, I need to write two equations, one of them expressing the intersection of the increasing line, y equals x plus 4, with the horizontal line, y equals 5, and the other equation showing the intersection of the decreasing line, negative x minus 4, with the line y equals 5. And you can see that here, to solve this equation, we subtract 4 from both sides and get x equals 1. That's shown up on the graph right here. And if I solve this equation, I'm going to get the solution negative 9. You can see you add 4 to both sides and multiply by negative 1, and we get x equals negative 9. Now, these equations are simple, and it's reasonable to say we can find the solutions without having to graph. But it is possible for the equations to get slightly more interesting, like this one. The absolute value of x plus 2 is equal to a half x plus 4. So on the right-hand side, we can imagine this is a function at the graph of the line y equals 1 half x plus 4. That's shown right here. And we can also see the absolute value of x plus 2 is a separate function. That's shown here. The slope is 1 or negative 1, and it shifts to the left 2. From the graph, I can see that there are two solutions, x equals 4 and x equals negative 4, highlighted here, showing the intersection on the left. The algebra says we have two choices. We can write two different equations. One, remove the absolute value and just leave it alone. The second equation is remove the absolute value, but take the opposite of everything inside of it. Now it follows that if I was to use algebra to solve this equation, which I'm going to subtract a half x from both sides, subtract 2 from both sides, and multiply both sides by 2, we get x equals 4. And it is logical that that is the solution because it's the increasing line with the increasing line. So the other solution, highlighted over here, is what I would find if I solved this equation. I don't have the algebra worked out, but suffice it to say that if I did solve this equation, I'll get x equals -4, and you can check by substituting -4 in here, or you can do the algebra, pause the video, write on a piece of paper the solution to this equation, and you solved it correctly if x equals -4. So again, what we have is a geometric representation and an algebraic representation. And what we're supposed to be doing now is using our graphing skills to help support the algebra skills where we need to get better. Another example is here, where we have the absolute value of x plus 3 is equal to 2x minus 2. The line 2x minus 2 has a slope of 2, y-intercept of -2. The absolute value of x plus 3 is 2 raised. It's the absolute value graph shifted to the right 3 units. And when I look at the graph, if I can get rid of this stuff right here for a second, when I look at the graph, I actually see only one intersection. It appears as though it's around 1 and 2/3. But if I was to do the algebra, I would show two separate equations. One where I remove the absolute value and leave it alone, and the other where I take the opposite of everything inside the absolute value. The point is, I only have to solve one of these two equations, because I only have one solution to worry about. The other solution, if I solve the other equation, I would get what's called a lie, a fake solution. It's right here. This dotted line is not part of the absolute value graph, but this dotted line shows the solution to the left-hand equation. So this is a lie, and this is the truth. And if you use your graph, you can save yourself the trouble of having to solve this equation and simply solve this one. And sure enough, distribute the -1, collect like terms, solve for x, and I find x equals 1 and 2/3, which is reflected on my graph. I don't even need to bother solving this equation because I can show on the graph that that's going to reveal a lie anyway. If I solve the left equation, I'll get x equals -1. And when x equals -1, the left side of the equation will be 4, but the right side of the equation will be -4, and 4 is not equal to -4. So x equals -1 is a lie. It's not a real solution to this absolute value equation. So in your work, all we have to do is look at any of these equations as a system of equations where y equals absolute value of x minus 3 and y equals 5. We graph those, we look for the intersection, and then we write two equations and solve. Try it.